Welcome to today's lecture on optimization algorithms or optimization methods, and in particular how they are relevant to chemistry. I would like to keep this about as interactive as we can get it in this online course. So whenever there's anything that's unclear or you have a question, please just text in the group chat so we can put this at the right place. So I'm Guido Feuer von Rudolph. I'm a postdoc in the group of Professor von Ehrenfeld. I'm a physicist by training, so please forgive me if my view on things is slightly colored in that regard. But I hope that we can get through this topic very smoothly. So let me start by mentioning why we care. And we care about optimization mostly because it's a very frequent problem class that you need to deal with, and scientists in general, but I would argue in particular so in chemistry. So there's two main particular things that you can consider that need to be optimized. So the one is energies. Think of molecular geometry, and you would like to know what's the most stable molecular geometry there is for a given molecule. Then one thing you need to do is you need to optimize that geometry. You can draw it, you can build it in 3D in the computer, but in any case you still need to find the minimum geometry, for example, to calculate vibration spectra or anything like. And the other flavor, the other direction which you can optimize is to find transition states. So transition state geometries linking reaction pathways, and the interesting part in this way is that these are opposite optimization directions. So to get a stable molecular geometry, you'll go downhill energy, you minimize the energy, and to find transition state geometry, you maximize the energy subject to some constraint. So for these two problem classes, for these two problems, that would be the energy that you need to minimize. Now, for those of you who are not going to do computational chemistry, but are more focused on the experimental side of things, you still need optimization. Maybe not the energy, but most likely you will spend a significant amount of time optimizing residuals. So residuals is the unexplained part of the numerical model of a fit. And imagine you do some experiment, you find some observables, and now you want to build a model based on that, which means that you have model parameters that you need to optimize such that your experimental measurements are explained the best way possible. So in that case, you would be minimizing the residuals to fit experimental data to some model. Oh, to fit the model to the experimental data, sorry. Another way would be if you want to fit a potential. We're going to talk about interpolation in some other lecture, but the concept is the same. You would like to recover a potential, you would like to recover an analytical expression for in this case, again, energies, in order to simplify other calculations, to simplify future modeling. And in this case, again, you would minimize residuals in order to force some functional form onto the data you have. And the last thing, for those who are going to listen to Anders' lectures on machine learning, there you have the same thing. You would like to fit a surrogate model onto to your data in order to simplify the explanation and to reduce computational cost. So whether it's computational chemistry or experimental chemistry, the picture is the same. Now, since we have a fairly diverse viewership this time, I would like to go through some definitions first so we all talk the same language. So the first thing is we minimize some coefficients. So whatever we minimize, whatever tunable knob we have, we're gonna collect in in the vector x, and the vector x contains sort of, several individual components. You see that here on the right. Let me maybe make this a little bit bigger. So here on the right side, you see the individual components that form the vector x, and this can be anything. This can be a molecular geometry, so for example, a position or an angle that span or forces the molecule to go in a certain configuration. This can be the fitting coefficient. Imagine you have some model as a quadratic function that you would like to fit to some data, then the coefficients of those polynomials would be the solution coefficients. Or if you think machine learning, then there could be model coefficients. It doesn't really matter. In the end, the most important thing is we have a bunch of scalar values, and our target function is just one scalar value. That can be, for example, the energy. If this is the molecular geometry and this is the energy, then the function we're optimizing is the energy given a certain molecular geometry. But if you don't fit an actual energy, but say a model function, then that could be the residual norm. So one way or the other, a measure of the accuracy of your fit. And for the purposes of today, we will assume that this function is smooth, meaning it's differentiable. And this is relevant because this means that the function, first of all, is continuous. So there's no sudden jumps in that function. And we will assume that it can be differentiated, because you can imagine the vast majority of optimization algorithms there are, they rely on gradients. It kind of makes sense, because you imagine you're standing in some landscape, and the question is, where is the deepest valley that you can see, which is equivalent to that problem. And then the first thing you're going to do is you're going to start walking downhill. And that's exactly what an optimization algorithm does. So just to simplify the problem in a sense that is typically justified for day-to-day problem, we're going to assume that the function is smooth and differentiable. This also has to do with the fact that the algorithms become much more complicated the moment you don't have any of those guarantees. Now, for each of those coefficients, for each of those entries over here, so for example, molecular geometries, say bond length, could be one of those, there is a domain which we're going to accept. So just a range of values that this particular X entry can assume. And we are going to say that we search a solution where this makes sense. So for example, a bond distance of 0.1 angstroms makes no sense. So we don't include that in our accepted parameter ranges. But we are going to live with any answer we get within that domain. So the formal way of writing this, for those who prefer the math notation, is we'd like to find the one vector X that contains all solution coefficients, that is part of that domain, but that minimizes one target function f, for example, the energy. And the solution that we get for this, the solution I'm going to call x0. Please don't confuse that with the first entry in the search lecture, because they are x1, x2 to xn, but x0 means one particular minimum, one set of coefficients that is a minimum. And another way to think about that would be, you find the one, if you prefer that notation, you find the one x that is always lower or at least equal to all other function values that can be assumed within that domain. So, of course, the minimization here can also be a maximization, but for all practical purposes, since this is the same problem just with inverted sign, we will talk about minimization in the next steps. So, okay. So, what is a minimum, a relevant minimum? So what you see here is on the x-axis a function, the blue function, and it has two minima. this one, and this one, and they are both local minima. Local minima meaning there is a one finite domain around that where all values are larger than the value at the actual minimum. And it's important to make this distinction because think of a molecule. In a molecule, you can have one metastable configuration, which then later on relaxes to something else, so another conformer. Or you're going to have many conformers in one molecule, but only one of them can be the most stable one. So every conformer is one local minimum, and from these two conformers, that one is more stable. Now, in this picture, we also have local maxima. It's basically the same thing with an inverted sign. So everything in that vicinity is lower in value than that particular point. From these two minima, however, the orange circles, only one of them is a global minimum, meaning that this is the absolute lowest one that you can have on that domain over which the function is specified. So this is a 1D function, so we go from here to here, and that's the lowest minimum there is. In chemistry, the relative position of these, in particular with regards to the local maxima, are often used to label how hard it is to get into that particular minimum. And this is called an attractive basin. So the idea is, if you come from this side and you actually overcome this hill over here, if you cross the local maximum and then go downhill from there, you're going to end up here. So this region, from this position onwards to the left, is the attractive basin of this minimum. And this position over here to the right is the attractive basin of that particular minimum over here. So you can think of it, if you have a molecular configuration, and this molecular configuration has a small attractive basin, then this is going to reach less likely. It's harder to actually reach that because by chance you have to come into a configuration that looks like that. Coincidentally, it's usually harder to escape small attractive basins. This, for example, plays a role if you think of protein folding. Sometimes you have this misfolding, and this misfolding usually is a very narrow attractive basin, but it can only be hardly ever be escaped. All right. So this is the attractive basin, which helps as some kind of tool to tell you how wide is this minimum. And we need one more thing. So another thing is the so-called quadratic region. And the idea is if you have some function, say the blue function over here, you can do a Taylor expansion around some point. And you can do that up to second order. If you do it, what you get is this red curve over here. And you see that in both cases, even though the local curvature is different, for some region around the minimum, this is a pretty good approximation. And we will use that in the discussion later on. So this is the region where, for example, the harmonic oscillator is a good approximation. Think of a bond. If you calculate vibrational frequencies, then you regularly assume that frequencies follow the harmonic potential, which to some extent is true, but as you know, is not generally true. So anharmonicity effects do play a role, but in optimization algorithms, it often helps to consider the quadratic region as a simplification of the matter. So the nice thing is you can do that with any function as long as it's smooth and differentiable. That's why we have this restriction at the beginning. Now, with the terms defined, we need to talk about algorithms. And the idea is, imagine if you would have such a function, what would you use in order to, what would you do in order to minimize some function? And there are two things you might want to do. That's what's shown on this slide. The one could be, I proceed iteratively. So I start at some point at this one over here, and then I figure out which direction is downhill. Then I move ever so slightly in the direction of downhill, and then I rinse and repeat. And this approach is called iterative, because you basically iteratively come closer to the minimum, and then at some point you decide that's good enough. So this usually means many small steps. And then the alternative idea is to do this directly. So no intermediate steps, but this means that you need to understand how the function looks like. And this approach is called a direct algorithm. So the idea is you first model the target function, and then you derive it, and you figure out where's my minimum, and you go there directly. Within the quadratic region, as I will show you, you can do that. Or if you have a function that actually has an analytical minimum, then you can do the same thing again. So that's, for example, something that machine learning methods try to exploit. There's important distinction, particularly if you read more about that in literature, then a direct method, so both words together, just mean that no gradients are calculated. That does not mean that you just use one step. All right, so let me start by briefly overviewing what kind of strategies there are. So what do people typically do in order to minimize that? And the idea is, I would like to give you an understanding, intuition for which algorithm works for which kind of problem and why. So we're not going to go into the gory details on how to actually implement many of those, because that's a pain. But we will focus on the core concept on how would you do it and why would you do it a certain way, such that whenever you encounter some kind of practical problem during your studies, that you kind of have an idea of which optimization technique you would like to use and why. So for all those optimization strategies, there are different families. And of course, within each family, there's a gazillion of different options. I'm going to talk you through the most popular ones. So the first one is the family of the so-called quasi-Newton or just Newton methods. And the idea is, you have a function, you calculate its derivative, the first and the second, so the gradient and the Hessian, or the Jacobian and the Hessian, if you like that terminology more. And the idea is, you then fit some harmonic function. So you have a value, you have a derivative, and you have a second derivative, meaning you can fit a local approximation to the function and then place yourselves into the minimum of that local approximation. You can't do that with the gradient alone, because if you only have the gradient, there is no minimum, right? So I can go in the direction of the gradient, and it will never come, it's never going to increase in energy if I just follow this gradient. But the moment you have a second derivative, you have the gradient that goes downhill, and you have the Hessian curvature that goes uphill again. So together, they give you a local minimum. Now, you can also follow the gradient, but then you need to do very small steps. And I'll talk about that later. So anything that actually calculates or estimates the gradient and the Hessian is called a quasi-Newton method. The other idea is to say the search space is huge. I mean, our 1D function is not a big problem, but imagine you have like a fitting problem and it has 20 parameters, and now fitting becomes awful. So the idea is, can we reduce the dimensionality? So can we say we only look at a certain subset of coefficients and optimize those first and do the rest later? That's often a good idea if you have something that lives on different orders of magnitude. So if you have something that is the dominating factor, then this one you'd like to fit first, and then there's like some auxiliary factors that go into the fit that you can do later. Then there are a family of quasi-random methods. They're called stochastic optimization, and the idea is draw a random point that might be a good solution, and then test whether it is a good solution, and then if at first you don't succeed, try again. So the problem in that case is you need to be very clever about how you do this random point selection, and that's the difference within that family. So that's why it says on the left side quasi-randomly, because it's not entirely randomly. And then the last strategy is fairly boring. It's called grid refinement. So the idea is you make a coarse grid, you go through all the grid points, you evaluate the function there. So basically for every possible set of combinations of coefficients, you evaluate the function, and then you look at, let's say, the region of the grid that typically gives low values, and then you do the same thing with a finer grid and so on. So that's a grid refinement strategy. It scales awfully. So the problem is that with higher dimensions, of course, the number of points you need to look at increases drastically. And so this is usually a method of last resort and hardly ever affordable. But these are the main strategies there are. And I've labeled them pure strategies because people quickly realize that you basically have two competing problems you need to solve. You need to find something that works largely okay, and then you need to refine this. So imagine if you're in this quadratic region where the harmonic approximation is applicable, going to the right minimum, to the correct minimum, is fairly easy. Many algorithms can do this in one step. And so what you want to do is you have this global problem, find some point that is kind of okay, so one conformer, but then optimize that conformer with gradients and then pick some other conformer. So for example, you might know genetic algorithms. I will briefly touch on that. And the idea in those cases is you do a few random points, and then for each of those points, you then follow the gradient or the Hessian downhill. So in practice, and very commonly, you use hybrid approaches where the first step is a more global kind of search thing, and then you have typically a Newton or quasi-Newton method that does the rest. Now, since almost all of these things are iterative approaches, I would like to use a certain notation to specify how the individual steps follow to each other. And we're going to use this notation on the left. So we're going to say in every step you're going to get a new estimate of x0. And so we have this an as the nth entry of the optimization step. So n-1 is the step before, n+1 is the step after. And we're always going to give an equation that gets you from an to an+1. So that's what the code would do. The idea is that as n approaches infinity, that the limit of this operation shall be the minimum. And that's typically the case. All right, now let's go through these pure strategies and have a look at why they are relevant and how they would work and when to use them. So if you first look at the figure at the right, here you see some 2D function that has minima. So here you see 4 local minima. And this is one example function where these approaches are useful. So you have the idea that you place yourself in one point, here, for example, and now you follow the gradient downhill towards the minimum. The problem with this approach is you need some reasonable initial guess. Imagine a molecule. If I take this molecule and if I cramp it together into, for example, just a line of atoms, and I minimize from there, I'm never, ever going to get this one molecule that I'm interested in. Just because there's no decent downhill pathway that would get you from benzene, but all atoms sorted on one line, to benzene as a ring structure. So you need a decent initial guess. That's also the same if you do curve fitting, particularly if you want to fit some exponential functions. They're very sensitive to your initial guess that you put into. The other thing is, you need pretty wide attractive basins. So this is only going to work if your quadratic approximation holds for a substantial part of the search space. Because effectively you are approximating the function with the second order term, so you're effectively approximating it with a quadratic function. And only if that actually converges, only then you have a good chance of reaching a minimum. So this is usually helpful if you care about local minima only. Think of conformal geometries. That would make sense to use one of the representatives of this family. And in all those cases, you need to make sure that you don't have noisy functions, because with noisy functions, so for example, experimental data where you have a given uncertainty of your value, this is going to go wrong very quickly because the gradients don't make sense. They are gradients including the noise. And the other problem is high dimensionality. And we're going to see that later in a bit more detail, but the main reason why you don't want to do that in higher dimensions, so say if your model has 50 parameters you'd like to fit, then this is because the Hessian contains the derivatives, the second order derivatives, but it contains all pairwise derivatives. So you have n, if n is the number of your coefficients, you have n squared minus n half coefficients that you need to calculate, or derivatives you need to calculate, and this scales awfully. Which means you need to do the Hessian evaluation in principle in every step. And that's expensive. So while in theory this is a nice idea, you want to do some shortcuts, and we're going to discuss them in a bit. So one of the popular representatives of this particular group are, well, Newton himself, which is exactly fit the gradient and the curvature. Then there is steepest descent, which is a little bit clever about the way how, so basically just fit the gradient and then hope for the best. And then there is BFGS and LBFGS, both of which try to use the explicit gradient because that's still cheap to calculate, but then approximate the Hessian. So they don't evaluate the Hessian, they have a way of keeping an approximate model of the Hessian. And LBFGS is the flavor where you even simplify the BFGS picture and you don't keep the full Hessian, you just say, if I know the major components of the Hessian, I'm fine. So in practice, it might make sense to go through this list from bottom to top. So if you can do it with LBFGS, you should do it with LBFGS. If you can't do it, then possibly BFGS is your better option. If that doesn't converge, then the steepest descent with a very small step size is guaranteed to converge on a convex problem, but it's going to make you wait because you need a very small step size to make that work. And for the bottom two, I gave you the SciPy function that you would need in order to minimize this. We're going to go through the Python part later on, where I show you how to use any of those algorithms as implemented in SciPy. Because to implement any of these algorithms reliably on your own is pretty hard, with the exception of Newton maybe. So the idea is let's use SciPy as long as we can. Okay, so what do we have? The first one is Newton's method. And in Newton's method, the idea is you can write this down, but effectively you can show that the next step depends on the second derivative and the first derivative of your target function, and it can be scaled by some step size s over here. So the idea is you are at one particular point, an, and at that point you evaluate the first derivative of your function, and then you evaluate the second derivative of your function at that point, And then you divide one by the other, multiply with some step size, and that's the direction you're going to go. Now, this is the basic assumption what would happen if you do a Taylor expansion around this point. And there are two main flavors where this plays a role. So the one is the flavor where you can change the step size. And that's kind of problematic because for the step size, you need to be clever about how you do it. Imagine you have a function that is very, very steep and then suddenly comes to an end. It's flat. If you just follow the gradient with a huge step size, you basically run around the minimum. You're going to end up on the other side. If you do a very small step size, you have to wait for ages. So you're going to need to compromise between those, and there are criteria on how to find those. But there are, I think, 4 or 5 main flavors, and we're going to talk about those. So the main variant you might find is where you can set the step size. Alternative approach is stochastic Newton, where the idea is you pick only certain dimensions, and within those dimensions you calculate the gradient and the Hessian, and then do this. And every time you select a new set of subdimensions you care about, which is particularly helpful if you have a large number of degrees of freedom, many dimensions, because then the second derivative is going to be expensive. And this has 2 main problems. The first one is, sounds nice, looks nice, but it's expensive, like really expensive compared to any of the other methods. So this expression here is the Hessian matrix, and this Hessian matrix scales quadratically with your number of coefficients, and then even worse, you need to invert that matrix. And that's an expensive operation. So first of all, calculating the matrix is expensive, and inverting it even more so. And of course, it's very slow because for practical purposes, you typically need a certain scale step size in order to make it work. Now, for all those algorithms, to give you an idea for which kind of problems they work well and for which ones they don't, I would like to show you these 4 plots. So you're going to see many of those. For each algorithm, you're going to see one. And the first one is we have 2 functions. So there's this function, the first row, and there's some other function, the second row. And the first function you see is just some quadratic, so some 2-dimensional quadratic function, which has a minimum, it's always the circles, and we have a starting point, which is always the star. And then the other one is called the Rosenborg function. That's a function which is designed to be hard to optimize. And again, this is a contour plot where this is the minimum valley, and it's very, very shallow, and the actual minimum is over here. So you see that the optimization algorithm, if you follow Newton's method, actually gets sent in the wrong direction. So it turns right uphill, and then later on actually reaches the minimum. And what you see on the right, so this is the actual optimization path, this red line, going from start to finish. And this is the deviation from the minimum that you get from this approach. So you see in this case, this goes just directly towards the minimum. So within a few steps, it systematically improves. So what you want from optimization algorithm is that this curve over here is as steep as possible for both cases. So in an ideal world, it's 1 step, can't be there. And in practice, what you see is here some regular slope, and here it needs some more steps because that's designed to be hard to optimize. So we're always going to look at those 2 problem families because these functions, they give you a little bit of an intuition for what kind of problems this works. So this is very well behaved, and this is a little bit mean. So let's see about that. So Newton's method was calculate first derivative, calculate second derivative. But second derivatives are expensive. What happens if we just don't do second derivatives, just go downhill. And this approach is called steepest descent. Kind of makes sense if you think about the name. The idea is the same thing. So you are at some trial position AN, you calculate the gradient at that position, you scale it with some step size, and now you have your new position. And if you do that, then you see this means I need to go downhill in each and every step. So if you think about this quadratic function over here, this goes perpendicular to the contour lines, and then in the end curves into the minimum. But if you compare this with the previous plot, which has the same axis dimensions for all of those plots, the convergence here is much slower. And it becomes even worse if you have anything that is not nice. So if you look at this function, you see this oscillatory behavior here around the minimum. The idea is, if you have any finite step size, then you're going to go past the local minimum, past the minimum in this particular direction, uphill again, and then you're going to have a new gradient. That's why you see this oscillatory behavior here, where you always miss the minimum and go forth and back. And you see convergence here is awful. So within the number of steps I gave it, I didn't even reach the minimum in the end. So this is not a very nice approach. And the problem is, in practice, you often see these oscillations here, and figuring out a proper step size is painful. One of the most promising approaches in that regard is whenever you have some gradient, you do multiple evaluations along that gradient in different step sizes until you find the minimum in this direction. So that would be called a line search. That's one way of doing it, but it's again expensive because you need to evaluate your function much more often. So in these cases, that's one major version of steepest descent that people actually use. And as I said before, it's mostly helpful if you have something which is tough, but where getting the minimum is more important than getting it in a fast way. As you can see here, because that's a very, very slim slope. I mean, it's going to converge eventually, it's just going to take ages. Okay, so this is the first idea. The first was, let's approximate the Hessian. No, the first one was, let's not calculate the Hessian. Anything you don't calculate is the cheapest way of doing it. But what if we approximate the Hessian? And that's what BFGS and LVFGS are doing. So they're still quasi-Newton methods because they use, conceptually, they use the Hessian, but they're clever in the way how they do that. And for this, let me quickly walk you through the math, because this equation over here, which is nice and simple, is a little bit more complicated in the context of BFGS. So the main idea is, it's still the same way as Newton's method. If you look at this equation over here, you're going to recognize that's the same update expression as in the Newton case. If we go back 2 slides, here you have AN is step size times inverse of the Hessian times gradient. It's the same thing we have here. This is the Hessian, this is the inverse, step size is 1, and this is the gradient. So your update step is the same thing. The difference comes into play when you figure out how to get this Hessian approximation and how to get the step size, which is 1 in this update equation. And you get the step size by line search. I mentioned that this is expensive, but effectively it's a very reliable way of getting a minimum in a certain direction. So this one here figures out a direction, that's a vector. This now is a scalar. So the idea is, by what prefactor do we have to scale this thing, this vector, such that we minimize our target function in this particular direction? That's some alpha. And so now you just say, all right, then my new step, the actual change I do, is just this step times this update method. So finding the next position, the next value in here, if you piece things together, is exactly the same thing as in as a Newton method. There's no difference whatsoever. So Newton method plus line search is BFGS. With the exception that you don't really calculate the Hessian. And that's where the different flavors, there's many sub-flavors of BFGS, where they come into play, and they largely rely on assessing gradient response. Because the gradient response is a measure of the change in gradients of the Hessian, of the curvature. So this gives you basically the curvature in the direction of your movement of your update steps in the direction of P. And with this, you can say my next Hessian is whatever I had as previous Hessian, plus some update formula. And the nice thing is you're not going to need to implement any of this, but the main concept is every step you do, you calculate an approximate of the Hessian in this particular direction, and then you use this to improve your estimate of how the full Hessian would look like. And that's the main idea in this case. So effectively, you start with some guess of your Hessian, typically the identity matrix, and then you improve your estimate as you go through with the optimization. That's actually pretty clever, right? So you only look at the path that is relevant to what you've been doing, and otherwise you just follow the gradient downhill. So in this picture, this concept looks like this. If you first look at the figures on the right, so here, this is actually 1, 2, 3 steps. That's the reason why this curve is so insanely steep. So regular quadratic function is optimized in next to nothing. And the reason why it actually takes additional steps is because BFGS doesn't have the Hessian. Remember Newton's method, where we have the full Hessian would go to the target in one step, because it's a quadratic function, and a quadratic function Newton can optimize in just one step, any quadratic function. But in this case, we don't have the full Hessian, we don't calculate the full Hessian. We start with some approximation that often it points in slightly the wrong direction. That's the reason why we have to do 3 steps. But 3 steps is quite good already, because you see that the moment you go here, you're not following the gradient anymore. The gradient would be perpendicular to the contour lines, but the movement you do isn't, meaning that in this picture, you have an improved estimate of the Hessian already after the first step. In the beginning, you just follow the gradient. That's why the first step is perpendicular to the contour line. So this one, awesome. The other one, you see, it still goes briefly in the wrong direction, and it has trouble getting this curvature over here, but it's very stable in doing so. And you see that this here converges very nicely and quickly after about 25 steps in this picture. So this approximate Hessian is a very nice thing. Conceptually and computationally, it's very nice. It has one drawback. It requires lots of memory. Because you need to keep your Hessian in memory, and you need to do all these update formulas, which typically require temporary variables, but again increase your memory. There's some clever ways around that, but the most clever way around it, again, things you don't calculate are the cheapest things you can do, is LBFGS. L stands for limited memory, and the idea is you only keep the dominating contributions of your Hessian matrix. It's an estimation anyway, so you can also estimate a little bit further in order to reduce memory requirements. So usually in practice, whenever you have the choice, LBFGS is what you're looking for. And in that case, that's typically for those things where it's stable, it's one of the fastest converging methods you can find. Now, there are cases where LBFGS won't save the day. This is in particular the case if you have a high dimensionality, because in a high dimensional problem, your Hessian becomes larger, you need more of them, you need to approximate more. Your fixed size Hessian subset is going to have hard trouble actually representing the true Hessian that you don't calculate. So in that picture, you want something a little bit more clever. So for anything which is low dimensional, so maybe, let's say, 10 to maybe 15 parameters, LBFGS is unbeatable. For anything larger, you want a subspace method. There are, again, several flavors. The most common in chemistry or in chemistry-related applications probably is the conjugate gradient method. And again, this is good if you have local minima, and again, if you have some reasonable initial guess. But now you can also do it if you have a high dimensionality. This used to be over here where not to use Newton. You still can't live with noisy functional variations, so you need something which is reproducible. And there are several flavors. The dominatingly used one is conjugate gradients. So let's have a look at how this one works. Now, conjugate gradients has one core idea. You follow the gradient, and then you say, this direction of the gradient, I have looked at it, I have done with it whatever I can, but now I would like to go in a different direction. So you enforce that subsequent optimization steps must not go in the same direction. They are not technically orthogonal to each other, so it's not completely orthogonal. They are orthogonal to each other with respect to the current Hessian where they are. That's the easiest way to think about that is they are orthogonal subject to some definition. It makes sense from a mathematical point of view, but it's not easily understood why you want to do it that way. Conceptually, the easiest way to think about that is imagine you want to go downhill, you follow one direction, then you turn 90 degrees, and then you follow that direction. And once you reach the end of that minimum, then again you turn 90 degrees and follow some other way, which in practice is going to mean some kind of zigzag motion. But the nice thing is that if you couple this with the line search, you get very substantial improvements every time you move. So it can't get worse. So that's what you see here. So first, you start with calculating the gradient. So that's the direction, the inverse of the negative of the gradient is the direction along which the energy or whatever target function you have decreases the most. Then you do a line search. So again, you figure out, okay, if I go in this direction, how far do I have to go? Where is my minimum? And then you say, all right, I just move that much. And then you make sure that any future step you make is orthogonal in some definition, orthogonal to all steps you have made so far. Which means that you need to keep a history of all steps you made, and because of the fact that computers only calculate with finite precision, from time to time you have to forget about all your past history and then do it again. So start from scratch and figure out a new direction. In particular, we have to do this after you used up all your dimensions. So imagine you are in a 2D landscape hiking and you want to go through the valley, then you can turn 90 degrees exactly once. Because afterwards, there is no direction left. So you can't go in the direction that the original gradient was, and you can't go perpendicular anymore, so you would stop. And at latest, at that point, you basically reset things and say, all right, conjugate gradient, start again. And the way how you do this, there are different flavors. The one showing here is the most common one, or commonly taught one, Fletcher-Reeves. And they all differ in conjugate gradients on how exactly they enforce their orthogonality. So the main idea is figure out alternating orthogonal directions along which you go. And that's a subspace method, because every time you only look at one particular direction, and then you look at some other particular direction that you haven't seen before. So how does conjugate gradients do? So this is our two example functions. So here you see 1, 2, 3 steps again. So this does very well in this picture. And then for the Rosenborg function, it does similarly to the LBFGS. So this means that for well-behaved problems like the top one, CG actually is going to be fast. And whenever you have something where you have low dimensionality and you just want something quick and easy, then CG very likely is going to do it. But CG has more, or is numerically less stable than, for example, LBFGS. So it might just fail optimizing something for bad luck because of the bad initial conditions. There are more flavors than just Fletcher-Reeves. The basic idea, the core concept is the same. They just differ in the way how they make sure to pick a new direction. And the typical solution, whenever you run into some numerical problem, where, for example, the line search in a certain direction does not reveal a new minimum, which could be the case if you have just for numerical reasons, your vector p points in the wrong direction, so uphill, then you line search in that direction will not reveal any minimum because you are at the lowest value that is possible in this direction. And what people typically do is they just say, all right, let's restart this thing. I forget about all my past search directions and I start from scratch again following the gradient. So you can make it work, but CG is usually helpful if you have high dimensions and if you want to be, say, acceptably unstable in high dimensions. So whenever you have something, say, below 15 coefficients, LBFGS is the way to go. For anything higher, you definitely want CG. Okay, so having established this, the next group, this was all, the first one was Newton with LBFGS. This one is a subspace method. The third one was the stochastic optimization family. If you look at this figure on the right, if you want to optimize a function like that, which from the chemistry perspective looks much more like a molecular energy landscape, then the algorithms we discussed, they are gonna have trouble. So the main reason for that is that they assume to be in the quadratic region, or at least that your function can be well approximated by a local Hessian. And for a function like this, that's not generally true. So it has many narrow minima, and finding one that is of relevance, that's hard. I mean, if you're in this minimum over here and you're gonna do some follow the Hessian, there's no way you're gonna end up in this minimum. It just doesn't exist. Now, in this case, you need a little bit more clever methods of doing that. And in particular, if you have something like large search space, think of conformal search in molecules very much looks like this. And so the first thing is you need to go from one attractive Bézin to some other attractive Bézin. Then you can use one of the common, say, LBFGS methods in order to go downhill again. But the moment you have something like this, you need a method to actually go from one attractive Bézin to some other attractive Bézin in order to further minimize your target function. Because otherwise you're just going to be trapped in one of the local minima and you're never going to escape that. So in practice, this means that whenever you have a large nonlinear search space with narrow attractive Bézins, then you want something that adds a little bit more randomness to the approach, how you go about it. There's two main flavors where this makes sense. So the one is simulated annealing. So the idea is you allow yourself to be at a certain distance from the minimum. So energy-wise, you basically float above the surface, and then you go in different directions, and you can overcome those hills if you're floating high enough. And then you gradually reduce how high above the surface you're floating until you end up in one of the minima, hopefully one of the lower minimas. And this concept is implemented in SciPy under the name Bazin hopping. Actually, this comes from chemistry, this idea. David Wales from Cambridge has popularized that a lot. And the other idea, very popular even outside chemistry, are genetic algorithms, or depending on what kind of flavor and the terminology you prefer, in SciPy they're called differential evolution algorithms. And they're also implemented in SciPy. So the basic idea is they go in the direction of picking some random points and then assuming that if that random point turned out to be useful, then maybe other random points closer to that one are more relevant than random points closer to this region where we didn't see anything. Genetic algorithms are usually fairly specialized. We won't talk about this in detail in this lecture. I will briefly present one of the libraries in the 4th lecture next Tuesday. Now, at least this kind of problem you can solve in SciPy using any of these two families. Now, or in members of the family for stochastic optimization. The last algorithm I want to present was this grid refinement concept. And this is helpful, for example, for a minimum like this. If we again look at the function, there is nothing happening for a large part of the search domain, and then there is a fairly narrow minimum that you'd like to reach. Now, grid refinement only makes sense if you can pay for it. And you can pay for it if your grid search has only a finite amount of points. Now, these function evaluations, they can be expensive. Think QM calculations or quantum chemistry calculations where you calculate the energy of some molecular geometry, then that costs a lot of compute resources. And that's why this is not going to be helpful if you do grid refinement techniques on that one, unless you have a very nice approximation that makes the function cost bearable. So if you have something which has low dimension and has bounds, so for example, not molecules, because I can stretch molecules as far as I want, whether they exist in that state is a different question, but in principle, the problem is valid for larger extents. And it's typically helpful if you can parallelize the individual points, because otherwise, if you have to do this in serial, you're never going to converge. Now, this is commonly used for 1D problems. For example, root finding in polynomials works like that. And in the other way, it's also implemented in SciPy. It's called grid search, where you define a set of grid points and you can evaluate the function on all of those and pick the lowest one, possibly refining that. And you can kind of guess by the name that this is called brute force. So it's a method of last resort that only makes sense if all other options are unsuited for the problem you have. Okay, so we talked about the different optimization methods there are, and we talked about Hessians and gradients. And they do exist in chemistry, both of which. So if you think of this target function as an energy, then this energy is a function of both molecular geometry and nuclear charges. So this means that the gradients would be one of two things. It can either be the gradient with respect to the positions, that's molecular forces. And this is commonly implemented in many QM codes. We will use in this and later lectures on numerics, we're going to use PySCF, which is a Python-only QM code that you can use, and it's actually quite okay. So it's commonly implemented, and those molecular forces can be evaluated by many programs, be it PySCF, be it Gaussian, or whatever. Now the problem is that usually you need to do special measures to do that, and it's a lot of work to obtain the actual correct forces. Luckily, all those QM codes do this for you. And the other derivative would be the gradient with respect to nuclear charge. So how would the energy change if you not were to change the geometry, but if you were to change the molecule itself, the atoms involved. And that's something that we do in our lab, how to calculate these and how to use that as a design guide in quantum chemistry. And these would be called the chemical derivatives. And the first one of which is the electronic electrostatic potential. These are usually not terribly commonly implemented in QM codes. I wish they were. Now, this was gradients, and there exist Hessians. And you probably know them in the context of normal modes. If you think vibrational spectra, then the individual lines you get are the result of the normal mode motions of the molecule. And they are also commonly implemented for at least the spatial part, because that's what relates to vibrational spectra. And you still can derive them analytically for many QM methods, although that's done less often than for gradients alone. And in this, many QM codes can also calculate that for you. In fact, in one of the later exercises, the one on matrix operations, you will calculate the normal modes and the vibrational frequencies yourself. Now we can say this is all fun and games, but what if there is no derivatives? What if we don't have this kind of information? And the nice thing is that there is a dead fast solution that in all cases you can think of is going to give you derivatives. But the no free lunch theorem strikes again, is not for free. The concept for that is called finite differences. Let me explain how this works, because that's what QM codes do if you don't have a real gradient, if you have to calculate this some other way. And you probably recall from high school math that the gradient is the limit expression of a small displacement along some function. And exactly this is what finite differences uses. So imagine you have some function over here and some point at which you'd like to calculate the gradient. And what you can do is you can calculate the gradient by putting yourself slightly forward and slightly backward of that point, and then put a linear function through it. And this would be called central finite differences, because you go slightly forward, slightly backward. If you want to be cheapskate and want to say, I don't want to have as many functional variations, then you can just go forward or just go backward, and then use these 2 points as a derivative approximation. But as you have guessed, this of course is worse than accuracy, because in fact, the forward finite differences between these 2 points are the central finite differences of that point, meaning farther away from the reference at which you're actually interested. So they're motivated by this limit expression figure, and you can do different versions thereof. They're all commonly implemented in typical libraries for that. You can also use more points forward and backward, so that would be higher order flavors. Now, the problem is, in this case, twofold. The first one, if you want to get the slope by this means that you need to be able to tell apart the function value here and the function value there. And since it's a limit expression, you would like to keep this displacement here as small as possible. But now you need some displacement in order to have a response of the function at all. Effectively, you're dividing a very small number by some other very small number. And this gives rise to numerical stability issues. So it's hard to pick one displacement here that is in a sweet spot between it's large enough such that you see something, that you avoid the numerical inaccuracies. There's also small enough such that you get a decent approximation of your gradient. So in this case, and that's exactly what you need to think about, and many libraries try to guess this for you. The other problem is it needs many calculations. So it's not only one evaluation here, but central finite differences needs 2 more on either end. So if your function evaluation is expensive, then finite differences are no fun. But the nice thing about it is it works in any case. It's a bit like using nail clippers to mow your lawn. It works, it's just the wrong tool, and it's tedious, but sometimes you don't have anything else. And that's where finite difference shines. So basically, it works all the time. You just need to have some points where you want to evaluate things, and then some weights to go with it. And this also works in 2D. Now, if you think of a 2D picture, if you want to get the derivative at that point, you can just calculate, evaluate some points around it, and then based on that, calculate the given derivatives. The problem is, if you do that in higher dimensions, you need even more points, because this is now 2D, so we not only need before and behind in one direction, we also need that in the different combinations. So this set of points, so all the points you evaluate in the context of finite difference, is called a stencil. And stencil is a measure that balances quality, so the accuracy of your prediction, and the cost. So for example, if you want to calculate any mixed second derivatives for this, so the second derivative dx dy, then you can do it either with all these 10 points, which is more accurate but more expensive, or you can do it without this point and without this point, which is smaller accuracy but cheaper. So the main context is, for this case, you need to be careful, decide, do I care about accuracy more, or do I care more about cost? But the nice thing is that if you choose the points, the weights come for free. So the main concept is you do a Taylor expansion around the point you're interested in, and then you solve the associated set of linear equations in order to get the points on how you would need to weight the functional values of those individual points. Again, libraries typically do that for you, which is nice. Okay, so we know what we can do if we don't have gradients. So there is a way to get gradients, but optimization completely without gradients usually is hard. You can do it. So for example, the genetic algorithms, they work without any gradients. They, strictly speaking, don't need some. They have their own strategies to compensate for that. But again, that's a more finicky part or approach to things. Now, whenever you do an optimization, including gradients, then there is a whole set of problems you need to be aware of. I would like to briefly discuss them. So the first one is, how do you figure out that your estimation is good enough? I mean, the moment you actually go through the, just follow the gradient, then that's nice, but following the gradient means that at some point you trust the gradient to be small enough. If you look at the function on the right side, then my gradient can be arbitrarily small. I mean, it's nearly flatlining here. It could be perfectly flatlining, but that's not a minimum. The minimum is down here. So convergence just based on the gradient ain't gonna fly, because you're gonna be stuck at some higher level point. So you want to calculate the Hessian for that, but getting the Hessian is expensive. So this convergence thing is hard to justify. And if you want to be super sure that you actually found the minimum, and after you found one, you need to calculate the full Hessian once. And then the full Hessian is going to tell you, based on the curvature, whether you're in a minimum, because in the minimum, the curvature is positive in all directions. So you could do that, and but the convergence criteria are hard, in particular since almost all codes typically stop on the gradient. In the second problem is this is math, right? And if you translate math into a computer, there's no guarantee whatsoever that the computer is actually going to do exactly what you wrote down on a piece of paper. And that's a general problem. It's particularly true in the context of this conjugate gradient approach, where your numerical errors quickly propagate, because every time you decide which direction is orthogonal, every time you're going to make some kind of error in this regard. So if you use conjugate gradients, this is going to bite you at some point. And for finite differences, you have the same issue again, because for finite differences, you have this balance between how large your step is and how much error in the gradient you are accepting. The other problem is, what about shallow minima? If you think of the Rosenbrock function, this function that had long stretched minimum, then actually converging to that one is hard because the gradient looks precisely like this, so it becomes very, very shallow. And then the other problem, of course, as mentioned before, is the cost of Hessians. So Hessians just typically mean that you need to do more evaluations, be it in just the matrix operations or be it in the actual function evaluation. And to give you an idea, so it's typically n squared. So for water, that would be 9 evaluations, and for caffeine, that's already 72. So for large molecules like protein, you won't be able to calculate a Hessian without any good reason. So often, since for many methods you only have finite differences, which makes this even more expensive, you typically want to have something that does not require the full Hessian, but at least some extent, some approximation to it. That's why, for example, molecular geometries, you'd almost always use either CG or LBFGS. There's two more problems. So the one is the curse of dimensionality, as it's so nicely coined. It's the problem that whenever you add more parameters, your search space increases very quickly and becomes less and less smooth because there might be more local minima. And this typically requires you to do very tiny optimization steps. So the larger your search space, the less likely it is that a Newton-based method is going to do you any good. That's the reason why many QM codes and quantum chemistry codes actually use CG in this case whenever they do minimization step, because then for that case, they give you, you are more reliable to actually converge to minimum. There's one general problem, which I'd like to summarize under preconditioning. So the point is that whenever you actually look at some, say, regression problem, some minimization problem, you would like to make sure that all dimensions contribute roughly equally to the problem. So you would like to have to rescale things until they become more similar. Think of this function plot that we had for all those optimization methods where you have this 2D harmonic function, and you would like to rescale it such that it becomes a completely symmetric case. Because otherwise you're going to have these cases of the very long, narrow minimum that makes sure your optimizer gets stuck along the way. So you would like to rescale things. Ideally, if you minimize something and you can afford to do so, then you would rescale each coefficient such that they contribute the same or have the same variance for each of the domain, for every part of the domain. So the common idea behind preconditioning is you take your problem that you have and transform it into something which has the same solution but is not the same problem. And this other problem then is better usable. And the nice thing is that many libraries can do that for you. So it's usually a good idea to rely on numerical libraries, except for educational purposes where you would like to re-implement function or optimization algorithms such as the Newton algorithm for better clarity. whenever you actually implement an algorithm from a paper or something, just make sure to not do any shortcuts, because the way it's written is usually designed to minimize numerical errors. If you say, I can rearrange things, then it's shorter, don't, because that's going to introduce more numerical errors. So typically the idea why some algorithms are needlessly complicated in the way how they're written is in order to minimize numerical problems. So either use a library or stick to that very enumeration. Okay, so how do you do this in Python? And I would like to show an example. So you have seen NumPy with Anders, and we have talked about vectorized mathematical operations in this context. Now, NumPy is a library for the data types, like an array, like a matrix. They exist in NumPy, and any operation you would like to do on those types, you should search for them in NumPy. Anything that contains algorithms, so optimization algorithms or anything the like, anything of that kind you would like to do in SciPy, because that's how the separation between the two very strongly related projects looks like. So SciPy generally has lots of scientific algorithms. I encourage you to just quickly browse through their webpage. The one submodule we're looking at is SciPy Optimize. And you've seen how to import a module, so you can say import SciPy Optimize. I'd like to give it some short abbreviation, because otherwise your source code is going to be littered with just SciPy Optimize. So the main idea is, for example, if you want to minimize something, you need to write a target function. And this target function, that should be the function you want to minimize. For example, least squares, it would be the sum of the square deviations. And then you need to specify some starting value for which you would like to minimize things. And then you can give this to SciPy minimize. If you want to maximize something, just flip the sign in your function. It does the same thing. So SciPy minimize, and now the one thing it always requires is a method. You need to specify how you'd like to do it. And that's the algorithm you need to choose, be it BFGS or LBFGSB, which means with bounds, or CG. For all those flavors, you have one method here. If you look up the documentation on SciPy Optimize, Minimize, it's going to tell you what options you have in this case. Then you need to specify where you would like to start. That's this x0 that we have over here. And lastly, you need to specify what function you'd like to optimize. So this is basically a minimal, complete example on how you would do that, how would you minimize things in NumPy or SciPy. And it's going to give you very many different output informations. So if you call this, you get a dictionary back, something like a dictionary. And you have the functional value, that's the last value this function has evaluated. You get the Hessian inverse, or at least an estimate thereof, the Jacobian, so that's the gradient. And you get the hint whether the optimization converged or whether you needed more steps. Then with .x, you have the actual result, the minimum that has been found. Now, you also get diagnostics to set into perspective how expensive it was to do this minimization. And this is what these three numbers tell you. The first one is the number of function evaluations. The second one is the number of iterations that your optimizer is doing. And this is the number of Jacobian evaluations, so how many gradients have been calculated. And you see that in this case, the gradients, they have been approximated by finite differences, because otherwise you wouldn't have a higher number of function evaluations here. And with the number of iterations, you need to be careful, because in some of the cases, the convergence check is only done in the step after. So NumPy reports too many steps that it had made in order to minimize things. So be careful if you need that. Okay, so this is the general picture. There's a question regarding accuracy. in the chat. So there's a question in the chat noting that whether Python is competitive in accuracy with C++ or Fortran regarding accuracy. And in fact it is, because the math behind that, the libraries are exactly the same. In fact, NumPy does all the heavy lifting in C or the Fortran libraries for that. So behind the optimization is OptPack or FitPack, the ancient Fortran libraries. But technically speaking, it's the same thing. So whether you do this in C, in C++, in Python, Fortran, doesn't matter. The accuracy of your floating point value is exactly the same. So it's a hardware limitation where you have that. It's not a software limitation. So while Python is typically not fully competitive in speed with C++ and Fortran, so in execution speed, it is completely on par in terms of numerical accuracy. Okay, so we have found this, the basic structure on the code, how the optimization would actually work. Now, sometimes you'd like to know how does the optimization proceed. And that's a nice way of, for example, checking how many iterations you actually needed. And this is how you do it. So if you think of the same example we had before, you'd now need to have an array, need to give it an array where these intermediate values can be stored. And the other thing is then you add this code, which, so the argument callback, which executes a function every time a new function is evaluated. So after every step, whatever function you give here is gonna be called. And what we do here is we just append this to the positions array. So sadly, there is no convenient way of doing that in SciPy Optimize. But if you follow this code example, this is going to allow you to trace the individual positions. What you get, if you well look at this list in the end, is the individual optimization points as the optimizer converges towards the final optimum that it presents to you. Okay. Keep in mind that the starting point in this list is not included. Okay, now if another practical problem that you're likely going to see if you want to fit things, optimize things in Python, is a least squares fit to some function. For example, if you have some energy function or your model function and you would like to fit the coefficients such that they match this to the original data that you have. And here's an example on how you do that in Python. So first, again, you load SciPy Optimize in NumPy. Here we just generate some data that we can fit. So XS is the X values of our data, YS are the Y values of our data. And the crucial thing is that if we want to have reproducible random data, we need to set the random seed of NumPy. So if you remove this line over here, you're going to get new numbers every time you run it. If you keep this line, you're going to get the same numbers every time. That's the reason why sometimes in exercises, in order to compare the values, we have this line. Please don't change it. And what we do here is we fit a linear function. So you see that I have my function definition over here is XS plus 0.1 of some random data. And this means that I just have this linear function. So if you think of the coefficients AX plus B, then A should be 1 and B should be 0. Now we have some random noise in here, and that's going to affect our least squares fit. What we need to write is one function, I call this linear here, one function that takes our coefficients that we'd like to fit first, that's something SciPy mandates, then takes the XS values and the values to fit, the YS. So first we can split this up and say the first argument shall be A and the second one shall be B. And then what we return are the residuals. So you always want to minimize the residuals, so you need to return the residuals. That's what we do here. So this is A times X plus B minus the true value YS. So that's precisely what we want. We want this, this in the residuals returned, and that's the function that in SciPy optimized least squares is going to reduce for us. So here we give it the function, and then we specify some starting points, which I start with just all zeros, and we give it the two X and Y values that we've specified here. If you do that, what you see here is that the fit reports the parameters in exactly that order. So A is nearly 1 and B is nearly 0, so that's the leading order term of that polynomial. In this case, we have fit a linear curve via regular regression to our specific target objective function. So those are the two main problems solved in Python, which might serve as an inspiration for any real-world problems you might encounter. So to summarize, we have seen different classes of algorithms, different classes of optimization approaches there are. We've described what these classes do and what's their key idea behind them. And based on those ideas and based on their performance, where are they more relevant and more efficient, and where would you like to choose something else? So we have the quasi-Newton methods like LBFGS, which works for low dimensionality but is fairly reliable, with subspace method as CG for large dimensions, where it's stochastic optimization if you have a very irregular surface you'd like to optimize. And we have grid refinement if nothing else works, and or if you need to look at all those points individually. We talked about the typical problems that you might see, so how to properly converge something, the fact that Hessians are expensive, and that there's numerical issues in the way how you deal with the problem. And lastly, we had looked at how things work in Python, so how to do both regular minimization and curve fitting with SciPy in Python. So with that, I'd like to see, are there any questions you might have right now?